Here's a challenge for you. Can you prove this theorem? Well, probably not, because this is the Riemann hypothesis. It's an open problem in mathematics, and there is a prize of $1 million for its solution. No one has claimed it. Yet, some people believe that AI models, if you just keep scaling them more and more and more, eventually they will be able to solve this problem and claim the prize. But my question is, how much will that cost? Because if we're talking about 7 trillion, 7 quadrillion, 7 Brazilian dollars to solve a single open problem, well, that's not so useful. We don't have this budget. So let's go back to the actual problem. This is a problem in type theory. And across all of type theory, there is not a single problem that requires neural networks for its fastest solution. We don't use AIs to sort numbers. So why do we assume deep learning is the optimal solution for this? What if there is an algorithm that, given a theorem, computes its proof much more directly, just like a sorting algorithm? The tool that I'm gonna show you today is a small step in that direction. It's a program and proof synthesizer that outperforms published solutions while being more capable and more general. I call it SupGen. On the surface, it's a proof assistant like Lean and Agda. So that means it's a tool that mathematicians can use to write and prove theorems. But there is a difference. It was built from scratch around a very, very fast enumerator of arbitrary types, and that allows us to do some pretty cool things. Let me show you. Here are some definitions. So this is a Boolean type, this is a natural number type, those are words of fixed length, lists, and some functions like negation, multiplication, addition, counting the bits set in a word, flipping all the bits in a word, and a modular division. So those are just some examples. And here are some proofs. So this is the proof of the congruence of equality. Is that how you pronounce that? And this is a proof that half of the double of any natural number equals itself. Okay? And yeah, like you probably noticed that this syntax here is very ugly, kind of scary. Of course, when we actually publish this tool, it will come with a syntax that looks more familiar and can be used to do normal programming. But for the sake of this demonstration, let's please ignore this ugly syntax and jump straight to the fun part, enumeration. So to enumerate all members of a type, it's very simple. We just give it a name, give it a type, and then send it to the type checker. And just like that, we can see a string of all natural numbers. But I mean, this example is simple enough. You can do that with a loop in any language. But the cool thing is, every type that you can construct, you can also enumerate. So here are all pairs of natural numbers. Oops. All pairs of natural numbers, or all lists of booleans, or all lists of natural numbers, or all lists of natural numbers and booleans, and any combination of that. I guess you get the idea. But those are simple types. There is something cooler that we can also enumerate. Function types. So here are all the functions from booleans to natural numbers, or from natural numbers to booleans, or from lists of natural numbers to lists of booleans, or again, any combination of that. And the good thing is that any definable function will appear in this string at some finite position. And that allows us to do some things. But before we do that, let's talk about dependent types, because we also have them and they are very useful. So here I make an enumeration of every word of length 4. So that's half a byte. And here I do the same enumeration, but now using a sigma type, also called a dependent pair, to restrict the space of this type to only include words that have exactly 2 bits set. So this is the result, right? So we can use those dependent types to prune down the space of a type in any way we like, arbitrarily, right? And that's pretty useful. Those enumerations are actually first class, so we can compute with them. So for example, here are like two enumerations, one of a function from numbers to number and the other of all numbers, right? And we can actually apply one to the other, and the result is a string of natural numbers. But this string is special because this is actually the application of every function to every number. If we can enumerate all members of any type, including function types, and if we can restrict those spaces arbitrarily, does that mean that we can also use this tool, as it is today, to find algorithms? And yes, we can do that. So here is an example. Here I make an enumeration from of a function from natural numbers to natural numbers, and I impose three restrictions, right? That f of 2 is 4, f of 3 is 6, and f of 5 is 10. And my question to you, a human, hopefully a human, an intelligent human, right? Which function is that? Can you guess? And I mean, probably yes, this one is simple enough. This is doubling the input. But what happens when we enumerate this space? And this is what happens. So now we get like a smaller list, like a smaller string of functions. All of those functions respect those restrictions. But the cool thing is, if you just scroll to the top and copy the first solution and turn it into a new definition, so what happens when we test it? So let's see, what's the result of f of 2? Well, it's 4, but of course it is, because we said it should be. And in the same way, like f of 3 is 6, and f of 5 is 10, because those are the equations. But what's f of 6? It's not here, right? So what's f of 6? It is 12. And what's f of 10? It is 20. And f of 100, it is 200, right? So the cool thing here is, by just giving this enumerator 3 examples, it managed to find an implementation of the most general notion of doubling a number, and it works for all inputs, not just like those 3 specific inputs that I have given it. Here's another example. In this one, I have a function from two numbers to a number and those 3 restrictions. So by the way, this one is wrong. So if you look at this example as an intelligent human, can you guess which function is that? This is adding the inputs. So what happens if we like list this space? And this is what happens. So we get all those functions. Most of them are, yes, overfit functions, but if we scroll to the top and get the first 2 results are very general, like actually the most general implementation of the notion of addition. So I can actually just copy this definition here and test in some inputs, and you can see that yes, this is actually adding those numbers, right? So 100 plus 11 is 111. That makes sense. So by just giving it 3 examples, we found a recursive addition function on natural numbers. And a point that I want to make here is that unlike other tools in the literature, and we know that because we tested them all, this is totally example agnostic, so we can actually change those examples to anything we like. Okay, it does not matter at all. Okay, and the thing is, that's not something that happens with other like tools in the literature, and that's something we realize because if you change the actual examples, then they stop working. So kind of those papers were like, the examples were a little bit cherry picked, I guess, because like if you change them, it does not work, and that does not happen here. Okay, you can have any examples and it just works. But now you might be thinking, okay, this is a very small function, right? So the question is, can we actually find functions here that you would not be able to find with a simple loop? And actually, yeah, so let's look at this example. So can you, again, a human, look at this and tell me which function is that. 1, 2, 3. Let's ask the enumerator, and it gives us this a little bit longer, right? Function. And if you just again turn it into a definition and try it in some inputs, perhaps you can get a better idea of what this is doing. So f of 1 of 10 and 10, 11 and 9, 2, 12 and 8, 3, 13 and 7. So hopefully now you can see that what this is doing is addition and subtraction and how it relates to the first argument. And it has done that in 0.06 seconds. No other tool in this same category in the published literature is able to find this program. Okay, you can like give them 1 second, 10 seconds, 1 hour, days, and they can't find this one. They will just time out all of them, right? Because I mean, it looks simple, but for some reason it's kind of complex. And it's actually like understandable that they can't find it, because if you take this function and compile it, like represent it on the binary lambda calculus, that's probably one of the most compact languages around. This one has 92 bits. And like just for the sake of the example, if we just count, right, not like run tests, not like do type checking, just count from 0 to this number. In the fastest CPUs that you have today, just counting would take 36 billion years, right? And yet the tool finds this program of this size in, again, 0.06 seconds. So this is not just a simple loop. There is something under the hood that makes this fast, which is like the whole point of this tool. Do very fast enumerations. And can we like go bigger? And yes, we can. So again, can you tell me which function is that? 1, 2, 3, yes, no. So let's ask the enumerator. And here, as you can see, yes, it takes a little bit more time. So in 4.5 seconds, it finds this function. Let's again turn it into a definition, test it in some inputs, and see what this is doing. So f of 100, 0, 101, 1, and then 2, and then 3, and then 4, and then 0, and then 1, and then 2, and then 3, and then 4, and then 0. So hopefully you can see now that this is an implementation of the modulus 5 operation, right? It takes a number and returns the modulus 5 of this number. And this function is actually kind of bloated, right? I mean, sure, it's no game engine, don't get me wrong. But this one, if we compile this to the binary lambda calculus, very compact representation, 140 bits. And just counting to that would take billions of times the age of the universe, right? Just to count it. So yes, definitely you are not going to find this function with a loop, right? With a simple loop. By the way, if you're curious, this function, if we compile it to Python, it will look something like this. So that's the function it finds. But again, perhaps you are not very patient and you can't wait 4 seconds. So how can we make this run faster? First, this parallelizes perfectly. So these runs were now in a single core CPU, but you can actually run it in a cluster and we'll get basically linear speed up. So that's very cool. Something else that you can do is that you can remember that we have a similar function in our code base, right? It's not the function we want, but this is similar enough, so that sounds useful. So what you can do is just give that function as a hint, okay, to the synthesizer. So you add this to the context, and then you do the search again. And just like that, it finds another implementation, which, if we try it, we can confirm that, yes, this is a correct implementation of the modulus 5 operation that works for all inputs, different algorithm, but works. And this one is using the function that we have sent it. So because of that, this search returns in 0.02 seconds, not 4 seconds. Now let's go to the main point of this demo, right? That is to prove a theorem. This theorem is no Riemann hypothesis, don't get me wrong, but it's a theorem that takes some time for humans to prove. And to show that, I will actually try to prove this theorem here live. And after that, we can compare the time I have taken against the time that the tool will take. So which theorem is that? This is a theorem that says that for every length and for every word of this length, if I flip all bits of that word twice, I'll get back the same original word as the output. And that makes sense. So let's try to prove this theorem. So first I will turn this into definition and start with an empty body. Now the type checker wants me to prove this theorem. It receives the length of the list, and I need to provide the proof of this equation. I will start by doing a fold over the length of the list, and this splits my goal in two. So one is the step case where I have access to the inductive hypothesis. Okay, so introduce it here and call it F. Now I need to receive a word with a size of n plus 1, so that's the step case, and I need to provide this proof. So I will pattern match on this word. Okay, that's what I want to do. I have many possibilities. I want to pattern match here. But this is actually wrong because this is a list of bits. So I receive the first bit, which I call the head, and the rest of the list, except the first bit, which I call the tail. And now I see the new goal. And the goal is to prove this equation. Now this is an equation on pairs. And because this language has an observational equality flavor, I can actually split this equation into two goals by using a pair here. So that's what I want to do. Now I have to prove this equation. And I will copy this here just to help you understand what this means, because my prettifier is not so pretty. So this is actually the compiler asking me to prove that for every boolean, the double negation of that boolean is itself. So it's the same thing, but now for booleans instead of for list of booleans. Makes sense. So let's turn this into auxiliary proof, and let's prove this one. So this one says that for every boolean, the double negation of the boolean equals itself. Okay, so I start again with an empty body, and I need to receive a boolean and compute this equality proof. So I'll just pattern match on the boolean, and here on the first case, I have to prove this goal, and I know that this is a function that receives the unit type and must construct this equality. So if I just pattern match on this will become false equals not false, which reduces to just false. So we will have false equals false, and that's true by reflexivity. So that's what I'm going to do. I'm going to pattern match on the unit type and complete this case with reflexivity, and that works. Now I need to prove this case. Because of how booleans are encoded, I actually need to pattern match here. And now I have two goals. The first goal is very similar to the other one, but now this is for the true case. So if I pattern match on this will become true equals not true, which reduces to true equals true. So I can actually prove this case in a very similar way, doing a pattern match on the unit type and completing with reflexivity. Okay, now I have this last case, and on this case I have a function that receives an element of the empty type, but the empty type has no elements, so this function can't be called at all. So basically this means that this case is impossible, it's not reachable. So I can complete it with an empty pattern match to signal that it is absurd. And just like that, I have proven the first theorem. This symbol here means that there are no more proof obligations as far as it comes to this sub proof, right? But what I was proving was something bigger, this one here, and I was in this position where I need to prove that flipping the first bit twice becomes itself. But that's what I have just done with this auxiliary function here. So I'll just call it on the first element of the list, and this proves this part of the proof here. Now I need to prove this part, and this part is the tail of the list. And again, my prettifier is not so pretty, but what this is saying is that for every possible tail of a list, If I flip the tail twice, it becomes the tail itself. So it's the same theorem, but now applied to the rest of the list, right? The tail. And because the tail is smaller than the list, I can actually use the inductive hypothesis that I introduced here to prove this part of the theorem. So that's what I'm going to do. I'm going to apply f to t, which is the tail, and just like that, this case is proved. The step case is solved. Now we need to prove the base case, the case where the list has a length of 0, right? And because of how I encode words, this is actually a sum type. So I need to pattern match here to see two different goals. So the first goal is, again, a function that receives a member of the empty type. This can't be called. This is absurd. So I just complete with an empty pattern match. And now I just need to prove this case. And this case is similar to the other ones. It's a function that receives a member of the unit type, and then I must construct this equality. And I know that once I pattern match here, this will become the empty list equals flip of the empty list, which is just the empty list. So this whole thing becomes empty equals empty. And that's true by reflexivity. So again, I just pattern match on this unit type and return a proof by reflexivity. And just like that, it works, it's proven. Congratulations, humans, you have proven this theorem. So now it's the synthesizer's turn. So first, instead of making a definition for us to prove, we make a meta variable for the synthesizer to prove. It will enumerate all elements of this type, but this is a theorem. So the elements of a theorem are its proofs. So if I just enumerate this space, what I get? Yes, I get the proof of this theorem. And if we type check this, we see that, yeah, this is correct. But this is the simple case. What about like the actual full proof? So let's again turn this into a meta variable, and let's ask the synthesizer to enumerate this space. So does it gives us a proof? And no, it's empty, because in this version, okay, of the enumerator, it can't include auxiliary functions itself. So let's help it help itself, right, and give it the function that it has written before. Okay, so with this little help, and now hopefully by enumerating this space, yes, we get not only one but actually 3 proofs, and the time it takes is 0.01 seconds, and that's actually just the time it takes to parse this file. So the search itself for this proof is instantaneous. So this is actually not a hard proof. A computer can actually do it very, very quickly. So here are all the three proofs that it has found. So I will use the first solution, okay, to make the actual definition, and type check it. I just need to give it like a name to this aux function that it used, a small bug on my implementation. But yes, it works and it's done, no proof obligations. And the sad part is that if we actually take this solution and compare it to the proof that I have made written manually with like human reasoning, yes, it turns out that the synthesizer solution, like this is my solution, and this is the solution by the synthesizer. And yes, the synthesizer has produced a simpler proof because it realizes that on this case I don't need to do all those pattern matches. I can just introduce a lambda and complete the proof by reflexivity. So now, what are some applications? So one application is to integrate with a theorem prover like Lin, Kind, Agda, and others that I don't know how to pronounce, to prove like boring sub-goals. Because one objection that people have against theorem proving is that, yes, it takes a lot of work, it's very laborious, so it's not really practical. So perhaps with a tool like that, we can make theorem proving more practical and software more correct in general. Another idea is to use this to make a synthetic dataset for reasoning models, because this tool does not produce just the proof, but it also produces all the steps to get there. Here we need to do case analysis. Here we need to do induction. So we can export a log of the steps to get from the theorem to the proof, and perhaps by doing this, like for a large list of theorems, we can make a very big data set with a lot of very different proofs and give it to AI model, and perhaps by training on that, it can become better at proving theorems and writing code. And I also want to use this to break LLMs out of doom loops. So we have GPT, it makes a simple program, it works, and then the program increases in size, and then there's a bug, and then it can't fix the bug, and now it gets stuck, right, in this doom loop that you can't get out unless like you have a very good developer that can actually debug the code. So the idea is, we ask the AI to create a theorem of something that it thinks is true, and it passes that to this tool, and this tool tries to prove that thing as a theorem. And by doing that, it will eventually find a contradiction, because like the theorem is actually not true because the function has a bug. But the thing is, when it finds this contradiction, it will be able to point to the exact location on the code base where the bug is, so it can like help the LLM get unstuck. Now finally, some closing notes. Why this is fast? Is this like solving P equals NP? Can I go ahead and just prove the Riemann hypothesis? No, like please. This is a very simple tool actually. It's just an enumerator, right? The reason this is so fast is that on this exponential space of enumerated cases, we share a lot of computations because we use a primitive from the ATVM to share all those computations. So yes, this is still exponential, but it saves a lot of time by this like computation sharing mechanism, and there's not much else to it. And it has some limitations. So for now, it only recurses on natural numbers. It's easy to fix. We'll do that soon. It can only find linear programs. This is also easy to fix, but not without blowing up the search space. So we want to address this in a more cautious, is that how I pronounce that, way, and soon. And again, it's still exponential, but so is O3, like that chart is log scale. So, I mean, the problem itself is inherently exponential, so there's not much we can do about that. And it can't learn, right? So there's no learning, there's no model. It just synthesizes a proof from scratch. And finally, it runs just in a single core so far, but it's ready to be parallelized. And we're actually building a cluster of Mac minis to do that, because if it finds those small or medium functions with a single core in 0.01 seconds, what will this be able to find when you have a cluster working in parallel to find those solutions? Even if it does not solve like big problems, I think it will be very useful for programming, filling all those holes in a code, like all those boring parts that you don't want to make. And like the more computers you have, the bigger those holes that it can fill will be. So I actually think this will be very useful, right, for programming, like directly, right? And finally, this little bit of a meme, but what if you turn this into a symbolic transformer, right? Like use this to predict the next token, because next token prediction is just a function from a list of tokens to a token. So this can be synthesized, right? And we can apply this synthesis problem to every position of a very big data set, collect and evolve like the definitions that come back from this synthesizer tool, gather the ones that work for more positions on the data set because they're more general, and then like grow it to the scale of a GPT model, and then like what happens? Well, what will this learn? Like what will this symbolic transformer be able to do? We don't know, but like hopefully we don't need to run to the hills, but more like use it to solve big problems like the Riemann hypothesis, or like making a whole game engine from scratch where everything is a cat, right? That sounds like an important problem to solve. Oof, let me chill down. That's it for today. Soon we'll have a playground that you can use this language. Hopefully by then, like the syntax will look a little bit less alien, right? So we'll have this playground soon. I think we'll have a lot of fun using this tool because we had a lot of fun. I have a lot of hopes for this tool because I actually think this will be so useful. So that's it for this presentation. Thanks for watching. Have a great day. Bye bye.